Okay, so the last lecture is going to be on continuous functions. So we've been doing compactness, compact sets, and now we're going to combine that with the notion of continuous functions. So this is something we already touched on before, right? We said we gave a theorem that said that f is continuous on a compact set, then the image is going to be compact, right? That the continuous image of a compact set is going to be compact. You remember there was that cube proof of it, right? That if you have a function on a compact set, and you're trying to show that the image is compact, well, you take your open cover. Somebody gives you an open cover. You pull it backwards to an open cover here. You use the compactness of K. Get a finite cover here. That gives you a finite cover back here, right? So constructing the finite cover, you can use the compactness of the domain to get the compactness of the image, right? And you needed to use the topological definition of continuity. So that was sort of a foreshadowing of what we're going to talk about. Let's talk first about the extreme value theorem. So we already proved the extreme value theorem, but now we can give a different proof of it. So if f is a continuous function on a compact set, then f attains its maximum value on K and attains its minimum value. So here we're thinking of f, right? We're thinking of f, right? You've got this, you have f going from R to R, right? And you have some compact set, and now we know what, we have some compact set over here, K, and what we're saying is that it's got to attain its max and it's got to attain its min. Does anyone have an idea of how this might work? Anyone have an idea of why this should happen? Let me put another piece up that we mentioned yesterday. If E is a compact set, E is a closed set, in fact, closed and bounded set, then the supremum V is contained, and also the infimum V is contained. Okay, so I'd like you to think about it for a bit and see if you can say anything about why this often happens. Anyone have any clues? Any ideas? Right. You've got. We're trying to show that if you have a continuous function on a compact set, then it attains its max and it attains its min. Okay, well let's just think about the max. If we get the max, certainly we can get the min, right? Okay. So you have a continuous function on a compact set. One thing that we know is that the image is going to be compact, right? So observe, right, f of k is compact, right? Compact, we know the same thing as closed and bounded, right? By Heine Barrel. So you need the image. You know the image is a closed and bounded set. Right? And so, Raleigh? So that's it, right? That's the end right there. Right? You say, well, the image is closed and bounded, so that means that K contains its supremum. Right? So, right, there's i.e., there exists an x such that f of x is the supremum of f. Right? In other words, there's a point where the max is attained. So that's the extreme value theorem seen from the point of view, from this sort of alternate point of view. And you think it's quite different from the proof that we gave earlier using the Bolzano-Weyl stress theorem. Bolzano-Weyl stress theorem is maybe, that's one way of looking at it, and here's another way of looking. Right? Once you have all this knowledge about compact sets, well, the extreme value theorem is kind of trivial. You say, well, look, the continuous image of a compact set is going to be compact. The end. Okay. Everybody get that? Yeah, Mia.
When you say f attains its max on K, do you just mean over the set K?
That's right.
There's a max and a min?
So what I'm saying is that there's a place in K where f attains, so where f of x is bigger than all of it. So there's a point on K where f of this is bigger than all of it.
Okay.
Okay. So there's
I got confused whether it was attains its max in general on K.
Oh well, I mean, right now we're just thinking of the function on K. It's not
Yeah.
It's not even defined anywhere else.
Okay.
Okay, so you've got this function defined on K, and Okay. So now we're going to introduce basically the very last notion of this course, and that's this notion of uniform continuity. So we're still talking about continuity on compact sets. So let's start off with sort of a motivation. Okay, so somebody gives you a line. Here's a function. It's a line. It has a fixed slope, and they say, I give you. So let's say that the slope is 1. Okay? Let's say that the slope is 1, and they say, can you find a delta, a distance, so that so here's my function, so that I'll say m is 2 to make it a little bit more interesting. So that whenever 2 points are within delta of each other, the outputs are within 1 of each other? Sure, right? So what's your delta going to be?
1/2.
1/2, right? Delta will be 1/2, right? Because certainly when two points are within 1/2 of each other, if the slope is 2, then the outputs are going to be within 1 of each other, right? Okay. And you notice that you can choose any 2 points, right? X and Y could be anywhere. As long as they're within 1/2 of each other, the outputs are going to be within one of each other, right? Okay, so a simple question. Right? Okay, so now let's think about a slightly different situation. Let's look at f of x being 1 over x. And let's say it goes from 0 to 1. So from 0 to 1, you've got this function. Okay. And I say, same question. Can you find a delta so that whenever 2 points are within delta of each other, f of x minus f of y are within 1 of each other? Okay, think for 10 seconds or a minute. Okay, what's the answer?
Between 0 and 1, you think?
Yeah, so for x and y in this interval 0 to 1.
Yeah, you can find a delta.
Can you find a delta?
Is it, if you have 1 over n, then,
What's n?
if you have like, okay, so if you have, can you have delta in terms of a function? Or does it have to be
The function is, here's the function.
I know,
It's a fixed
but
function.
if you have like say you have one x value 1 over n, and then your y value is 1 over n plus 1, then they would be within 1 of each other.
Yes.
But you can't have delta in terms of a function.
Well, you're looking for a delta that works for any 2 points. Okay. What we're saying is that can you find over here? We found a delta, and it had this great property that if you take any 2 points and the distance between them, if you take any 2 points and the distance between them is less than 1/2, then the distance between the outputs is less than 1. Can we do something like that over here? Can you find a delta so that whenever 2 guys are within delta of each other, their outputs are within 1 of each other? What do you think? Ichen?
No, I'm just thinking because on the left side it goes to infinity.
Yeah.
So as the x goes to 0, the slope goes to like deeper, like.
Yeah. The slope is increasing, right? So I mean, this guy here, it's also going to infinity, but the slope is constant, right? But over here, the slope is actually increasing. The slope becomes infinite as you head towards 0, right? So the answer is no. The answer is no. There's no delta that's going to work, right? Because if you say, I think a delta of a half will work. Okay, and you say, okay, well then, I take this guy, I take 1 point, I take x and a half, and I take y really close to 0. Right? I take y really close to 0, or I take y at 1/4. I take y at 1/4, and then you see that that it doesn't work. Okay. Now, if somebody says, well, I take delta to be 1/1,000,000th, say, maybe if they're in 1/1,000,000th of each other, it's going to work. Still not going to work, right? Because you go to, you'd say, well, if I take my x to be 1 millionth, and I take my y to be 1 over 2 million, well, the outputs are 1 million distance apart, right? You get 2 million over here for the guy on the left, and 1 million at the one on the right, and you see that you fail very badly. Okay, so the answer is no, right? You can't find a delta that works for all pairs. Maybe you can find a delta that works for if you fix one of the points, right? Certainly you can find a delta if you fix one of the points and say, can I stay within one of that point? The answer is yes, right? Because the function is continuous, right? But if you're saying, I'm not allowed to fix points, and I want to find a delta that works for all pairs, then the answer is you can't do it. Okay. So what we're asking, what we have in this case, and what we fail to have in this case, is a stronger form of continuity, and that's what's called uniform continuity. Okay. So, right. Okay. So definition. Here's a function. If for every epsilon greater than 0, there exists a delta such that whenever x minus y is less than delta f of x minus f of y is less than epsilon, then we say, so this is on some set. F is uniformly continuous. So uniformly continuous on the set. And this kind of continuity turns out to be crucial in some later results, which you may see. I'll try to talk about a little bit before the class ends. Yeah, Ichan.
I know this is different than like continuous
Yeah.
everywhere. Like I don't quite get what part makes it different.
Okay. So this function was continuous at every point,
Yeah.
right? What would continuity at every point means? It would mean that for each x in your set, you're continuous, right? Given any epsilon, there exists delta such that if y lies in the delta neighborhood of x, then f of y, if x minus y is less than delta, then f of x minus f of y is less than epsilon. Right? So it looks very similar, right? Okay. So what's the difference? The difference is that this delta is allowed to change for each x, right? The delta is allowed to change for each x, right? So this is for all x and y in your set. Whenever you've got two guys close to each other, then the outputs will be epsilon close to each other, right? But here the delta to make it completely clear, you say, well, this delta depends on epsilon and it also depends on x. Okay, this delta is a function of epsilon and also of x. But here, the delta is just a function of epsilon. It doesn't depend on x at all. Okay. So back in the case of the line, right? You can choose a delta of somebody given epsilon of 1. You can choose a delta of a half, and that half worked everywhere, right? Okay. Here, somebody gave you a 1, and if you said I'm going to fix a point, Well, then you can find a delta that works for this one point, right? As long as guys are within, you know, 1/6 of a half, then, you know, the outputs are going to be within one of each other, right? But that's not going. That doesn't work if you move the center. Okay. So you can think of this as sort of a centered result, right? A centered and point-specific result. This is a point-specific result, and then this is not a point-specific condition. Okay. Okay. So you can probably guess what I'm going to prove. What am I going to prove? Not the extreme value theorem. Not again. We already have 3 proofs of it. That's enough. Can anybody guess what will be the last result of the course? The central limit theorem? What course do you think that we are in? Bose-Einstein wire stress? Bose-Einstein wire stress?
No.
No. No. No. But actually, to be honest, I'm going to end on something that's sort of like a super Bose-Einstein wire stress thing, if we get to it, if there's enough time. Okay, so the last result. Remember, this is all under continuity and compactness. Okay. So the last result is the following: if f is continuous and k is compact, and in fact, what? F is uniformly continuous. So continuity on a compact set implies uniform continuity. Okay. So if we took our 1 over x here and we constrained it to a compact set, then it's going to be uniformly continuous. So whatever compact set we constrain it to. As long as you're continuous on it, then you're going to be uniformly continuous. Okay. Okay, so here's the proof. Right? We have continuity, right? We have continuity at every point. Okay. Right. So fix epsilon. Right. We're trying to show that there's the delta that works for all pairs. What we have is that for each point, there's a delta that works. Right. So we know that for each x and k, a radius delta x, so that f of the delta x ball around x lies within the epsilon ball of f of x. Okay, that's continuity. So here's our compact set again. We have it's mapping somewhere, right? And for every point x, right? If we take an epsilon ball around here, well, there's a delta ball around here that gets mapped inside there. Right? That's continuity. Actually, let me use epsilon over 2. Let me choose the delta so that it maps inside the epsilon over 2 ball. Okay. Certainly, we can do that.
Sure.
I'm gonna choose my delta so that it maps inside the epsilon over 2 ball. You can choose it to map inside the epsilon ball. I'm going to let it map inside the epsilon over tuple. Okay. So that's you'll see why I need this in a second. Okay. So right, we fixed our epsilon. Look at epsilon over 2, right? Look at the epsilon over 2 neighborhood. There's some delta neighborhood that gets mapped inside the epsilon over 2 neighborhood. Right? That's just continuity. Okay. Okay. So at each point we have these delta neighborhoods, right? Right? And we're hoping that we're hoping to find some distance, right? We're hoping to find some magical distance, some length, right? So that every pair, as long as they're within that distance of each other, the outputs are going to lie within epsilon of each other. Okay. Okay. So what we do is we cover every point in here with the delta balls. Okay, so cover K with these delta balls. Right. Every point we're going to cover with the delta balls. The delta balls are constructed so that if you lie within the delta ball, then you're going to lie within the epsilon. You're going to lie within epsilon of f of x. Right. Every point has this thing. Cover every point.
Does that mean that are some values that aren't in K in the delta balls that cover K, like on the edges?
There's a neighborhood. Yes.
So even those points get mapped into the epsilon neighborhood?
Yes. 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 So our function is continuous. Let's just say for
Like over K?
yeah, let's just say that f is continuous on R. Okay. So we don't have to worry about sort of some details that we don't want to worry about. Okay. So every point is covered by this delta neighborhood, some delta neighborhood, and those deltas can change, right? That's the thing, right? Some of them may be bigger, and some of them may be smaller, etc. Okay. Well, you know what we're going to do next, right? You take a finite subcover. K is compact, so there exists a finite, decent finite subcover. Right. What do I call this? I call them P. Okay. Oh, actually, let me take it back. Cover K with, with the half intervals, with the half. So take half of those guys, take the radius, divide those radius by half, and cover each guy by the half ball. Right. So there's some decent subcover consisting of these half intervals. Right, so there's some finite number of points. Let's call them P1, P2, to Pn, and their half delta neighborhoods cover all of K. Okay. take delta to be the minimum of all these radii. So 1/2 the minimum of the delta pi. Okay, and that will be, that delta is what we're looking for. Okay. That's the delta we're looking for. Okay. So why is that? Why is that the right delta? Let's think about it. Right. Suppose that, say that you have 2 points, P and Q. Distance from P to Q is less than delta. Okay. Does anyone see how it's going to finish up?
If that delta is less than all the other neighborhoods, then P and Q will always be less than, will always be less.
That's okay. That's okay.
If delta is the minimum of those those neighborhoods, or of those deltas.
Minimum radius, yeah.
Yeah. Then and P and Q are always within the minimum radius, then they'll be within all of the radii.
They're going to be within one of the balls.
Yeah.
Right? That's what you're saying. Exactly. So say, well, look, P is going to lie. P must lie P must lie in one of the P is going to lie in one of these balls. Right. So there's a PK, and P lies within the delta over 2. P lies in the delta over 2 ball. Right. But can you finish it? It's your last chance to finish something.
Can you say what makes sense about Q?
What do you say about Q? Well, Q, the distance from Q to P is less than delta, right? And delta was smaller than. Right, so you don't want to say this exactly the same thing, right? If you said that Q was close to some other guy, that's not going to be what you want, right? But you can say that you do know this, right? So how does it go? So what do you say about it? This is. Katie?
Does it have to do with the diameter of the wall
in the image, the distance. So remember what this delta was, right? It was chosen so that anybody within the delta here is going to be within epsilon over 2 of f of pk, right? Anybody within the delta ball is going to be within epsilon over 2 of f of pk.
You just construct the delta ball.
Okay, so we have the delta ball here, right? And Where's Q? Q is within the delta ball, right? Because the distance from P to Q, right? The distance from P to Q is less than this delta, but delta was smaller than all of the half radii, right? Delta was smaller than all of the half radii. So this is delta piece of K over 2. And the distance from P to Q is smaller than delta, but delta is smaller than all of these half radii guys, right? So since that's true, we see that Q also lies in the full radius, the full delta radius ball. Right? So both of these guys, right? Both of these guys lie within the delta ball, and so what does that tell you? That tells you that the distance from f of p to f of q is what? Smaller than, and this is a good way for analysis course to end. Well, no, not yet. So each of these guys lies, there's P in here and there's Q in here. So the outputs lie here, F of P and F of Q. What's the distance between F of P and F of Q? Epsilon, of course, epsilon will be the answer, but why is it epsilon?
Epsilon 1 plus epsilon over 2.
Epsilon over 2. Epsilon over 2 plus epsilon over 2, which is epsilon. Yeah, so that's the end. Right, because of the triangle inequality. Right? This is smaller than the distance of f of p to f of k plus the distance of f of k to f of q, which is epsilon over 2 plus epsilon over 2. So that really is the way for an analysis course to end, with the triangle inequality and the fact that epsilon over 2 plus epsilon over 2 is epsilon.